All right, cool. Let's get started. Welcome back to MLFL, everybody. Today, we have Dana Arad, who's a CS PhD candidate at the Technion, advised by Jonathan Belinkov. Her research aims to improve our understanding of the internal mechanisms of language and vision language models with a focus on information flow and factuality. Dana has interned at Amazon and eBay and is a fellow of the Ariane de Rothschild Women Doctoral Program. And with that, please give a hand to our speaker today, Dana.
Thank you. Thank you for this introduction and thank you for inviting me to give this talk. It was very nice of you. And I hope you will find this research interesting. And also, I unfortunately did not have time today for one-on-ones. But if any of you find this interesting, please reach out and I will be happy to set up individual talks. Um, yeah, and also on that note, so I'll present today two of our recent papers on SAEs. Are people familiar with SAEs? I'll give also a brief introduction. But this is not my main area of research. So mostly I work on multimodal models, so mainly vision and language, and recently also audio, music, and I hope to start working on video models as well. So if any of that is interesting to any of you, also please reach out. Um, yeah, that's it. Uh, One last thing, I would prefer this to be a discussion, so please ask questions at any time. Stop me if you don't understand anything. I'm in no rush to make it through all of the slides. I just want to have like an interesting discussion. Okay, so what will we talk about today? Why is it not okay? So I'll give some background on SAEs for those that are not familiar with it. On polysemanticity, how do we do steering with SAEs, and how do we interpret SAE features? Then I will go on to talk about uh, our recent paper on distinguishing between input features and output features in SAEs, which I'll define later. And then we go on to do persistent unlearning with SAEs. Do you hear me all right? Is everything okay? Perfect. So, polysemanticity. Basically, our models want to learn and want to encode more concepts than they have parameters for, right? This is true basically for any model uh, that we currently have. And this leads to polysemanticity, which is the phenomenon that neurons must represent more, some neurons at least, must represent more than one single concept. And I like to show how this looks like in CNN in the context of computer vision because I think this is easier to understand. So this is a work kind of like old from 2017 on just visualization of CNN filters, okay, unrelated to SAEs. But what they found is that some features seem to represent multiple concepts. So, for example, when they visualize this feature, they see that it lights up on images of foxes, of cats, and of cars. And when they use their methods to represent, to visualize each one of these concepts separately, then we can actually get the images of car parts or cat faces or fox faces separately. When this happens in language models as well. So if we look at examples of polysemanticity, we might see examples like, okay, this neuron lights up on both text in Korean and digits and punctuation marks. And we can see many examples like this. This essentially, what happens in our model is that our model uses the dimensions that we give it, but they are unable to represent all of the concepts, right? We would want to represent a concept as orthogonal as possible, which would mean use each direction that we have in our latent space to represent some concept. But we're unable to do that. So we represent our concepts as sparsely as possible in our space, right? This leads to the superposition hypothesis that our features form an overcomplete basis of our latent space, meaning we can think of the directions in our latent space as weighted sums of our true underlying concept space. Does that make sense? Cool. This is what it means mathematically, right? So it means that if we have some k true features, and I use quotation for true, k features, we can think of each feature having a direction in our space, and then we would want to have a weighted sum of these directions to form our latent space. So for each representation, there is some coefficient that we would take and multiply every direction for every concept, and that would reconstruct our latent space. Use them to find these true underlying features of our latent space. Um, So what do we have? We have our encoder and some decoder. We take our latent representation from some layer in our model. In this case, we're working with SAEs trained on the residual stream. So we just take the latent representation after some transformer block, and we want to pass it through our encoder, some nonlinearity, to obtain our feature directions, our feature coefficients, which are these values, fk. We multiply them by the decoder, which are our direction vectors, and we train this model to reconstruct our latent space. So we train this with just reconstruction loss and a sparsity loss. Is that okay?
Question.
Yes.
So is it only reconstruction loss in the latent space or also in the loss measurement in the downstream task of which the transformer model actually trained on?
That's a great question. So most sparse autoencoders are just reconstruction and sparsity as well. But you're right that they don't incorporate the full loss of the model. So like uh, an example like that would be to also pass this reconstructed value through our model and get like a cross entropy loss, right? Propagated back into the SAE. I agree that would be better. That would be much more expensive, right? To train, because it re would require like this is very, I would not say easy to train because it does have like a bit of details that make it difficult to train. But in terms of computation power, in terms of what size GPU do you need to train this, this is kind of lean, right? Versus backprop through your entire model, which may be very, very large. That might be a problem. Yeah, but I agree that that would be better. Any other questions? Cool. So, these features were shown to be more interpretable and more monosemantic compared to polysemanticity that we talked about in previous work. And the main application that people have come up with for these auxiliary models is steering. So let's say we found some feature that is responsible for some concept, let's say chocolate. Then we want to give our models a sentence, right? I love. And during a forward pass, we can amplify the coefficient of this chocolate feature. And then we see that our model completes the sentence, I like chocolate, right? Or starts talking about how much chocolate is the most amazing thing in the world. So this is kind of the most practical thing that people have found that SAEs are useful for. And this is particularly useful in safety applications. For example, bias mitigation. So this is from a work done by Anthropic, and they have found this feature in Claude 3, which is responsible for gender bias awareness. And then they give the model the following input. Human, complete the following sentence. I asked a nurse a question and the assistant outputs. The nursing profession is a historically female-dominated field. Using the pronoun she to refer to a nurse is common convention. However, it's important to note that there are also many male nurses, and the gender neutrality of certain professions is increasing over time. So we see that when we amplify this feature during the forward pass, our model becomes more gender bias aware, right? And then that was the consensus for a while. And then came this work from some researchers at Stanford, which I really like the title that they gave their work. Steering LLMs, even simple baselines outperform SAEs. And I think you kind of get where this is going. So, some details about what they did. So they took 500 pairs of concepts and features from 2 layers of the model, and they performed steering, and they measured their steering using a mean of 3 metrics. So first, they want the generation to be fluent. They want the generation to follow the instructions given to the model, and they want the generated text to adhere to the concept that we wanted to steer towards, right? So if I wanted the model to talk about gender bias awareness or chocolate or whatever, then I want to actually measure that the generation fits that concept. And they evaluated a bunch of different methods. So they started with kind of the gray methods are the unfair comparison, right? Because we can prompt a model to talk to be gender bias aware. But then this is just a user thing, right? This is not a property of the model. We cannot control it. We can add system prompts, but the model itself does not, like, this is very much user dependent. And on the other side, we can have very kind of like very intrusive, let's call them methods, right? The very that change the model. So these are all kinds of fine-tuning methods. And fine-tuning just changes our entire model weights or some of our model weights in a very like too aggressive way. And then they compared a bunch of representation-based steering methods, which is kind of what we mean when we say steering. And the most basic way to do representation-based steering is difference in means. And I guess some of you are familiar with it. So what this means basically is that we take representations from a positive group and a negative group. We take the mean representation, we subtract the 2 groups, and we say, okay, this is the difference between positive and negative. And if we want to steer towards the positive, let's just add this vector to all of our samples. This is the most basic way to do steering. And what they found is that even this most basic method outperformed SAE. Okay, so you can see SAEs got really kind of a terrible score on their benchmark. And even this simple method got around double the results, right? But then let me take you back to the example that we saw. And this was kind of the state of the project when I was like, but steering with SAEs work, right? I was playing around with it for a few months at that point, and it does work in some cases. And we have this example from Anthropic, and we have a few more examples that empirically it does work. So what's happening here? And this is kind of where we this project kind of settled in place. So the question you might be asking yourself is, how do we select the features for steering, right? So let's talk about that for a few moments. So the most common way to select the features or to interpret features and then select based on that is to look at their activations. So activation basically means look at the input text that make this feature light up, right? And we can see different magnitudes of activations. And we can just look at them and see kind of what this feature is about. So when we look at activations, we see that this feature looks like it's relevant for engineering, right? So let's try steering with this feature. This is from GemmaScope SAEs 16K Gemma 2B, if you're interested. So let's give the model the text, "I once heard that," and steer kind of strongly with this feature. The best way to become a better writer is to write for other people. Interesting. Then let's try again with even stronger steering factors. "I once heard that the best way to write write great copy was to look at the other way companies solve the same problem. I once heard that the way of love solves problems." This doesn't say anything about engineering, right? But kind of seems from the activation that it would very much be the case. And then going back to that Anthropic work, they noted something in their takeaways. So there's a disconnect between features activations and the resulting behavior. And what they noted and what we also noted is that there's no inherent reason why features activation context would directly correspond to its effect on the model outputs. So what they said essentially is that if we look at these activations here, yeah, they have some correlation, but this doesn't tell us the activation do not tell us what the feature will do once we intervene on it. So this is kind of the point where we kind of understood what we have in hand. And this is our work, which was accepted and presented in the last EMNLP in China. SAEs are good for steering if you select the right features. And this was a collaboration with Aaron Mueller, who's now at BU. He was a postdoc in our lab jointly with Northeastern, and Jonathan Bengov, my advisor. And what we did here is we identified two roles that SAE features can have. So we differentiated between input features, which are features that correspond to, they identify some pattern in the input to the model. This versus output features, which have some human understandable causal effect on the output. And these are not the same. This is kind of the main claim here. So let's go back to our engineering feature. Um, any questions, by the way?
I had a couple of questions.
Yeah,
Firstly, on the Axbench results that you had shown, uh, what do those numbers correspond to? Or like more
yeah,
broadly, what does like better steering mean here?
yeah. So they measure three notions. They use LLM as a judge, and they measure the fluency of the text. So how coherent is your generated text, right? Because you want to keep the language coherent. You want to follow the instructions. So this is the instruction score. And you want your generated text to contain a concept. So you have all three of these metrics, and then you take the harmonic mean of them. Is that okay?
Yeah, I think so.
Okay.
And
And then what we see here is that SAEs, so like think of these metrics all you would like generations can get values of 0, 1, or 2, and then you take the harmonic mean. So score of 0.1 is really, really low.
I have also a question.
Yeah.
If we say steering SAEs, let's say, works if we choose the right, let's say, features, is it also probably like input dependent? So for one input, you might steer or need to steer one feature, and for a different input, you might to steer a different, obviously, feature, right?
Definitely.
Okay.
Definitely. So think of, but steering is very much context dependent, right? Because you would want to steer towards gender bias awareness. So you would have to find what representation in any of these methods. You would have to find what representation, direction, SAE feature, any of these methods, what corresponds to gender bias awareness, for example.
Thank you.
Any other questions? Okay.
Yeah, how coefficient sensitive is steering? Like, in your experience?
I'm sorry, can you repeat it?
How coefficient sensitive is steering?
Um, what do you mean by sensitive?
Like you see these results like on X bench, and I guess choosing the right features. Do you think coefficient matters?
Oh, you mean let me go here, the steering factor, you mean, right?
Yeah,
This
yeah.
number. Yeah. Okay, keep this question in mind. We'll talk about it in a few slides.
Okay.
Any other questions?
Feel free to skip this one also if you end up covering it later. But it seems like you suggest that there's some SAE features where like what you look at the heat maps also has some correspondence with what happens when you try to control it. Like it's causal in some way. And there are others that are just sort of observational. You classified it as like input and output. But if you just picked up some SAE feature, is whether you got one or the other just sort of luck of the draw? Or is
Interesting.
there
Okay,
anything more to
yeah,
it?
let's talk about it. So let me just define what I mean by them, and then we'll talk about that. That's a great question. So input and output features. Now, let's talk about how we define them. So we wanted to use two observations that we had in order to characterize them. So first of all is this activation pattern, as you noted correctly. So we saw that activation patterns are different for input features and for output features, and I will show examples in a minute. And we also, so for me, it was really important to characterize output features with a causal effect. So actually measuring the causal effect that they have on the output. So these are both of the factors that we kind of took into consideration. So let's define this. Input features, we looked at the activations, and then let me add another bit of information, which is the logit lens tokens. And the logit lens tokens in this context, I mean, logit lens in general is a method for interpreting model internals by projecting them to the unembedding space. And here what we can do is we can take this vector that is the direction of our concept in the latent space. And this has a dimension that is the same as the latent space itself, right? And we can use this to project this in the same way to the embedding matrix. And this is important to note that it's not input dependent, right? It's a property of the feature itself, of the SAE itself. And you might be wondering, okay, but like logit lens, we do it on like hidden representations. It kind of makes sense why it would work. Why would it work for SAE weights? And the answer is that many papers show us that it does make sense to apply basically anything within our model that is of the correct shape. We can multiply it by the unembedding matrix and get a projection to the vocabulary space that is meaningful. So people have shown it. Arad showed it on the latent space, on attention weights, and if I remember correctly, MLP weights. Tokel, which is also I was part of that team. We showed it multimodal and multimodal systems that we can take from the text encoder and project internal computation to diffusion models, to gradients, basically anything of the correct shape. So these are these tokens, which I'm hoping also convinces you that it makes sense because we also see this engineering come up in the logit lens tokens. Questions on that? Cool. And we saw what happens when we steer with this feature, right? So when we steer really strongly, we kind of get this hint of engineering, right? The way of love solves problems, alternative approaches. It's kind of a hint of engineering. And then we have other examples. So when we look at this feature, again, activates really strongly on instances of the word primary. And we can see that the logit lens tokens, again, are variations of the word primary. When we steer using this feature, we see the following text. Findings shows that and care, treatment, school, these are words that seem like they come after the word primary. Primary school, primary treatment, primary care, primary function, right? It kind of seems like steering makes the model think that it saw the word primary in the context and outputs the following word. This is in contrast to output features, where we see a different effect. So here we have this feature where the logit tokens are mentioning words like crime, corruption, violence, terrorism, and so on. And when we steer with this feature, we get really coherent steering. So findings show that 76% of parents have experienced abuse from their child bully, and so on. She saw a lot of violence and corruption. We get coherent steering, which is what we wanted, right? And when we look at the activation patterns, we see that they are no longer very, very concentrated around the specific tokens in the logit lens. We see that they are more spread around them, right? We can see that the word that corresponds to the logit lens is no longer the most activated token, but the token before it, right? We see this more spread around pattern. And this is kind of the differences that we wanted to measure, both in the activation and in the causal effect. I'll define it now more formally, but that's also a good point to stop for questions. Cool. So basically, we define two scores, but they measure exactly what I just told you as motivation. So for input score, we collect some set of activations over some large corpus. And in practice, we take the pre-computed activations from Neuronpedia, which are really useful if you're working on SAEs, and I highly recommend using them. We take the maximally activated token from each sample. So here it's engineering, engineering, and engineering with capital E. Then we take our top K logit lens tokens, and we ask how many of these tokens are in the logit lens. And for example, for this feature, we get an input score of 0.756, which is extremely, extremely high. Output score looks like this. We run a forward pass with a neutral prompt, and these are the actual values that we use. So we use the prompt in my experience, and we amplify the feature times 10. And we record the ranks and the probabilities of the top K logit lens tokens after this intervention. So if our tokens were crime, corruption, violence, so on, then we look at what rank and what is the probability of these tokens at the final output of the model after this intervention. We take the maximally ranked token, and we set the score as rank times probability, but because they're opposite scales, so we normalize the rank, right? Because rank lower is better and probability higher is better. Normalize the rank, and then you can think about it as rank times probability. So for this case, the output score is 0.451, again, extremely high. And this goes to the question that I got earlier about the factor. Does it matter what factor I use? And this is essentially what we saw here. So like you can also say, of course you're measuring the effect on the output, right? Because of course features that you identify using this method will be good for steering, right? Because that's what we measure. But the thing to remember here is that we measure only one prompt and only a single steering factor. But this property of writing to the output is something really fundamental in a feature. So like a feature either writes to the output or doesn't. So it kind of doesn't matter if we test it with what steering factor we use as long as it's like high enough, right? So we would capture some sense of the feature, and we can always also take this number to be stronger and stronger to catch more of the outliers. But essentially, this property is really fundamental, and we only need one prompt, one steering factor, one forward pass, and we catch this property. And it's used in any context that you might want after this. which is what I think makes it cool. So any questions on this? And did I answer your question from before? Cool. So the next question, after we quantify these two roles, is what do they look like across model layers? How do they emerge across model layers? So what you see here is for Gemma 2B, 2B, and 9B. And you can see the median input score and median output score. And also we take the 25 to 75 quantiles. So if you look at outliers, you would essentially fill out the whole box, but we're interested in the trend. And what you see is that for the first kind of 60% of the model's depth, you see input score is the dominant role, right? So mainly we would see input features. And then around 50% of the model depth to the final layer, we see output score emerging, meaning that we see output features in our SAEs. And this is really cool because this aligns really well with what we know about models in general, right? So we know about transformer models that they go through layers of feature engineering, right? Representation building. And towards the end, they move to a stage of writing to the output, right? Preparing the token for generation. If you're familiar with LogicLens, you can see this, for example, by the correct token appearing a few layers before the final layer. And again, many papers that show this kind of split in phases within a model. So this kind of shows us that this is another validation that we captured what we wanted to capture, if that makes sense. And then you might notice this gap in the middle, right? So the middle kind of seems like there's already a drop in input features before there's the rise in output scores. So there's a gap. And what happens in this gap? And this is, I think, a really interesting question for follow-up work, which I'm not working on currently. So if any of you are interested in that, I'm happy to talk about it more. What happens in those middle layers, right? So we know from previous work that we expect models in these middle layers to perform things like store and retrieve knowledge, right? Parametric knowledge is something that is happening in those middle layers, and other more complex functions. Some computations are happening in those middle layers. And makes sense that our metrics don't capture that because we designed them to capture something different. But I think it would be really interesting to keep developing metrics that find these more complex computations in the middle and see if we can find SAE features that identify them. They can be really useful for many applications. Any questions before we move on? Cool. So we already talked about Axbench, and I guess you knew where I was going with it. So we went back to Axbench, and we wanted to see to verify essentially if we upsample features with high output scores, do we get better results? Which is the whole point of our work, right? So we reevaluate on their setup, right? So we use their features that they have selected from two model layers, and we evaluate using the same protocol, three metrics that are based on an external LLM as a judge, which measure fluency, instruction following, and concepts. So these are their scores. Let me remind you that we saw really low values for SAEs. And first of all, just by reevaluating the same features exactly in our setup, we notice that we get higher scores. And I think that was also a question earlier about the sensitivity of the evaluation. So the evaluation is sensitive. right? In this case, we wanted to compare to their results, so we went with it, but we do note that it is higher. And we propose, we have different experiments where we use different metrics that are not based on LLM as a judge, that are more reproducible, let's call it. They capture different information, but we do show the two points of view. But this is like, yeah, it is when using LLM as a judge, we add some randomness to our metrics. So this was on the question that we got before. But then let's apply our filtering. So essentially what we want to do now is to filter out any feature that has output score below some threshold. So we filter out first output score that is lower than 0.0001 and then increasingly bigger thresholds. And we see that when we filter out score features with a score below 0.1, we get better results than Axbench on layer 31, and we get really, really close at layer 20. And this is compared to their method, right? It's not out of the baseline method that they showed, but they proposed in their paper, Reft R1, which is, to their claim, the winning representation-based steering methods. So we get, with using SAEs, the same SAEs that they used, but just filtering out features that are not output features, and we get better scores at layer 31. So this kind of goes to show that SAEs can be good for steering if you choose features that are designed, or are designed is not the word, but are capturing this property of writing to the output. So this is the takeaway from this work, that SAEs are useful for some applications, and that we kind of have to think about how we choose our features based on our specific application, right? So if we want steering, then we need to select our features by thinking of their causal effect, right? It's kind of naive to expect that if we select our features based on their activations, the activations will tell us something about the causal effect, right? It doesn't necessarily mean that. And that's what people have been doing. So this is what we propose here. And then there are other types of features that we expect to find, but we didn't get into it in this work. So we talked about knowledge features briefly, and that may be, so I mentioned that we explored only the residual stream SAEs, but maybe if we train SAEs on MLPs specifically, and there are SAEs trained on MLPs, we would find knowledge features. Same goes for attention SAEs. Maybe we would find something like function features, right? So like name mover heads. And then suppression features, which is something that we also know that language models are doing. So in the very final layers of transformer language models, we know that they suppress some tokens. So also I think if you're familiar with the IOI work, it also pops up there. So we know that models don't want to give too high probabilities to specific tokens. They want to kind of keep all probabilities around not the middle, but like not have extreme probabilities. So we expect to find some features that are kind of opposite of output features, right? Suppression features. Just to name a few, but we can think of many, many others. So this is it for the first work. How much time do I have? Do I have an hour?
Looks like about 20 minutes.
Okay, that's fine. Yeah, so like an hour total. Okay, so we have enough time for the next one. And then um, we sometimes don't want to encourage our model to generate something on a specific topic, but we want to avoid it, right? We want to steer away from some topics. So think, for example, of biosecurity. So let's say you want to not allow your model to give advices on how to create some harmful biological materials. So we can use steering and apply negative steering factors to steer away from these concepts. But this is, again, kind of user dependent, right? Or maybe inference time method. And for unlearning, we might want something that is more persistent, that you apply once to your model, you have a new model that has no knowledge of biosecurity material, and now you can use it safely in your downstream applications. So this is the second project I'm going to present today. It was led by Tomer Ashuach. He's a PhD student in our lab. And this is again in collaboration with Aaron Mueller, who's now at BU, Martin Tutek, who is now at Zagreb University, and Jonathan Belinkov. And it's titled CRISP, Persistent Concept Unlearning via Sparse Autoencoders. So we go about doing utilizing SAEs to do unlearning. And the first question is again, how do we select the relevant set of features that we want to use for this unlearning? And what we use here are two corpuses, two corpora. We have a target corpus, which contains harmful examples of biological unsafe content. And we have the benign corpus, which contains, in this case, scientific papers from biology domain. And we pass them through our model and then through our SAE. And we collect the activations of features on the target corpus and on the benign corpus. And we plot the activations. So we look for features that activate more strongly on the target than on the benign. And you might be thinking, I just spent the last 30 minutes talking about how choosing features based on their activations is kind of not ideal, right? But let me remind you that activation do capture something about the topic, right? They don't go into the resolution of is this reading from the input or writing from the output. But we did see in all of the examples that the activations are related to the general topic, right? So if a feature is responsible for reading engineering, it still lights up on engineering in the longer context of the sequence. So activations in this context, I think they make sense to use. So we collect these activations and we plot and we look for features that activate more strongly in the target than on the benign. And what do we find? So the purple features here are features that activate equally in both sets. And these are features like this, concepts related to organizational research methods, which makes sense because both of them are scientific papers, either general biology or on biosecurity. For the target features, we see things like this, terms related to viral infections in mammals, exactly what we wanted to capture. And for the blue, these are the least interpretable, unfortunately, in this analysis. And we find, for example, numerical data associated with statistics and various topics. And this kind of maybe an artifact of the data that we use. Maybe the benign corpus contains more papers with statistics than the target corpus. The blue were unfortunately less interpretable, but we do see for the purple and for the red that they do make sense with what we wanted to capture. Then we want to use these SAE features to perform unlearning on our base model. So we're no longer passing through the SAE in our forward pass like we did with the steering, but we want to use them to make some persistent change in our base model such that we will only need to run the base model for inference. So we use a combination of three objectives, which are based on ELM, which was the work by David Bao's group at Northeastern, led by Rohit Gandikota. So the first objective is the unlearning loss. We want to suppress the activation of the target features on the target text. So we want to essentially mute the features that are responsible for exclusively for the target corpus. We want to essentially make them not activate anymore. So we pass the text through our model, we collect activation on the SAEs, and we optimize such that the activations will, to suppress the activations. Then we want a retention loss. So another objective is to keep our model as close to the original knowledge that it had as possible. So we want the benign corpus to behave exactly the same. So we pass the benign corpus through our model, we collect the hidden activations across all layers, and we want these hidden activations to remain as close to the original as possible. The last objective is coherency. So we want our model to retain its coherency. What we do here is we take a small corpus of really difficult examples and really, really specific examples. We pass them through our model, and then we take again the hidden activation, and we want to preserve that as much as possible. Here, we use a coherency loss that the coherency corpus, we use a set of what we call educational examples. So we still take examples that contain knowledge about the specific biosecurity material in question, but we change we want our model to answer some output such that the output is still relevant to the topic, but is no longer harmful. So, for example, the immunity response to infections include both innate and adaptive immunity, something, something, right? So something very informational that you would read on Wikipedia, for example. This is unlike ELM, where they use the coherency corpus of avoidance. This is harmful. Let's change the topic. Let's talk about something else. Let's find something more interesting. And we will see later what is the effect of this choice. So any questions about this, the three objectives? Okay. So we use a weighted sum of them, which doesn't sum up to one, which is, I know it's weird, but this is the numbers that we got. And we optimize our model using all three objectives. And you can see that the retention loss is by far the strongest objective, right? And I think with any changes you want to do, any changes of this nature, you know that when you want, the most difficult thing to do is to keep your model from catastrophic forgetting, right? From a catastrophic change in the model such that it only knows your new facts and forgets everything else. So the retention loss is very dominant, with a very small unlearning loss and very small coherency loss. So here you can see examples of our method CRISP compared to the previous methods. So these are original model generation. These are RMU, which is the paper that proposed the data set that we use, WMDP. And ELM, which is the method that I mentioned, and us. And you can see that both RMU and ELM have some very obvious artifacts. So RMU is very prone to repetitions. You can see that the sentence that begins with the most common carcinogens repeats. Here we can see it repeating 3 times, but it repeats like 10 times. The most common, the most common, the most common. Just repeats the same sentence over and over and over. ELM has takes this avoidance that we saw. On one hand, they wanted the avoidance, right? That was the coherency loss. But it takes this avoidance to extreme in some cases. In cases where it fails with, I'm not going to talk about that, blah, blah, blah. I'm going to talk about insert random topic here. Complete avoidance, which loses the coherency. And in contrast, our method in these cases is able to produce educational texts that are somewhat relevant to the topic, but remove any harmful implications of talking about that topic. And I think it also goes to show that choosing the correct coherency loss is really critical, because if you want to change your model too far from your starting point, you might get these artifacts. But if you change to something that is closer to the original outputs, so changing from answering a more informative answer about carcinogens to a less informative answer, but still on the topic of carcinogens, you get better results. So here you can see some numbers, and we measure this across different axes. So you can see that what we wanted to do is get a better result in the overall metric, because you can have a model that unlearns everything, right? But The problem is to balance all of our objectives together. So you want to both unlearn, but retain your knowledge and your general knowledge as well. That's why we measure MMLU. And you want to also have a model that is fluent and that is talking about the relevant concept still. So that's why mainly we view our method as like we care about the overall sum of our metrics, and our method does achieve a big improvement on that. But of course, the work is not done, right? Unlearning is not solved yet. And our method also has its own flavor of failure. So if we said that RMU is prone to repetition and ELM has this extreme avoidance in some cases, our method has its own flavor of gibberish that people have told us that looks like kind of math, like a latex language. Um, and unlearning is not solved yet, but I think we did have some increased performance and increased improvement to the model. So the takeaway is that SAEs are useful for some application. I think for unlearning, they're extremely useful, and there's still more to uncover for that. And when we choose our features wisely, we can get to really good results. And then, if you think of the future directions from the previous work, we mentioned things like knowledge features. And if you think of the target feature set that we found here, maybe if we take that and we strip away the input features and the output features, maybe that's also another way to find this knowledge features, these more complex features that maybe exist in SAEs, maybe SAEs are not the tool for, but this combination of these two approaches might help us find some additional insights. So with that, I want to thank my collaborators. So Tomo, who led the second work that I presented, Aaron and Martin and Jonathan, great collaborators. I really recommend working with all of them. Feel free to reach out. I'm happy to talk about any of these two papers, any other topics you want to talk about. And that's it for today.
Thank you so much. Are there any questions from anyone?
Yeah, I had a question related to like selection of SAE features. Do you think that it matters like what percentage of the examples the feature activates on? Like in terms of, I guess, how monosemantic the feature is? That's question number one. Question number two is like, what do you think about steering multiple SAE features together? Like, if you like steer, let's say, two SAE features, like one of them is in the earlier layers, I guess that's an input feature, and one of them is in like the output layers. So what do you observe in those cases if you have done that, I guess?
I'll answer the second question and then remind me what was the first question. So that's really, really interesting. I tried for a while steering with multiple SAE features, and I think, okay, and the results are, they confused me. Let's say that. So on one hand, SAEs are not built to capture multi-layer interactions, right? They're a very local tool. You train them on a single specific layer. So they don't, and we said that with no multi-layer objective. So they are not meant for capturing these multi-layer interactions. That's one. But then if you do try to steer with multiple features, maybe even in the same layer, but across layers, I did see many examples where that improved the performance. So even for features that are not necessarily output features, we did see more complex behaviors that maybe if you do amplify features that you didn't think have a strong causal effect, maybe they have a second order effect or a third order effect, something like this. Maybe you could make your model still have some signal. So that's something that we didn't get to explore fully in this work, but I think is really, really interesting. I will say that SAEs maybe are not the tool for that. So like it's interesting to understand multi-layer interactions, but like as a scientific interest, right? If you want to truly capture the multi-layer interactions of your model, SAEs are not a multi-layer tool. Um, so this is on that. And then remind me what was the first question?
Yeah, the first question was basically, uh, did you have a criteria for like what percentage of the overall examples that particular feature activates on? Like not
Yeah.
just the activation strength itself, but also like percentage of examples.
Yeah, but for you mean for the second work, right?
I guess also for the first work, like yeah, apart from input score and output score, if there was any correlation, I guess
Scores
with
actually, the scores kind of capture that. For uh, the second project, we used activations for an initial set of features and then applied the optimization on top of that, right? So because we used that within the training, then we allowed our models kind of a second layer of choose whether this is a candidate set of features, but then the optimization kind of is allowed to choose how strongly does it need to like take the signal from every one of the features to optimize all of the objectives together. So we didn't take that directly into consideration, but kind of in the overall scheme of things, I think it is get like the signal is there.
okay. Thank you.
Thank you.
I had another question about the difference in means results that you had. So, uh, do you think that even with the difference in means and I guess the other method they had, I think reft, uh, do you do you think the same trend holds that you just get better results when you work with the last 1/3 of the model layers?
So another result that we have is that I didn't show it here. I don't know if I have it on the slides, but it's in the paper that if even if you only select features from the um, last layers of the models, still filtering out based on output scores is meaningful and improves your steering performance. Because as I mentioned for the plot about the emergence across layers, we only take the 75 to 25 quantiles,
Hmm.
but there are a lot of features with extreme scores in all layers. So even in those late layers, filtering out based on output scores is meaningful.
That
And I
makes
guess to your question about the difference in means, I would guess that it does work better on later layers, but then I don't have an intuition on like how to improve it based on like this distinction between output and input. Because another thing to say about input and output is that it might not exist in the original model. So it might be an artifact of kind of over separating of the SAE, right? It may be that the direction for chocolate is one direction in our model, but because we kind of train our SAE to over decompose our latent space, possibly, because we need to set the sparsity, like the amount of features we choose it as a hyperparameter. So it doesn't, we don't give our SAEs the possibility to kind of optimize their number of features. So it's possible that for some directions we over decompose our latent space, and from one chocolate direction we create two input and output chocolate directions. We didn't test for that, so it's just an intuition level. But that also might explain why difference in means are kind of sometimes easier.
that makes sense. Mm, if there aren't any other questions, then I'd like to once again give a hand for our speaker today.
Thank you very much for having me.
Yeah, thank you so much for giving this talk.
Bye.